Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Beam Bending Failure, and it is going to provide you fundamentals of the area moment of inertia and also the bending failure test of a timber beam. I am going to give you an overview of what I am covering today's video. First at all, it is a bit of background to the topic, and then focus on calculating the area moment of inertia and the bending failure test before wrapping up with conclusions. Okay, we have a plank of wood which we would like to use to cross a canal. It has a rectangular cross-section, and so we could either use it like we have done, or we could rotate it onto its side. Intuitively, we can tell that the plank will be stiffer if the load is applied to the shorter side of the cross-section. Some cross-sections are much more efficient at resisting bending than others. The further the material is spread from the bending axis, the stiffer a cross-section tends to be. The cross-section on the right has more material located far from the bending axis, and so is better at resisting bending, even though both cross-sections have the same area. This concept of resistance to bending can be quantified by calculating the area moment of inertia, which is also sometimes called the second moment of area. The area moment of inertia reflects how the area of a cross-section is distributed relative to a particular axis, and so is a measure of how much resistance the cross-section has to bending. Now we are going to take a detailed look at the area moment of inertia. Let's start by seeing how it can be calculated for an arbitrary cross-section. The first thing to note is that the area moment of inertia is not a unique property of a cross-section. It quantifies the resistance to bending about a particular axis, and so its value changes depending on where we place this reference axis. We can approximate the area moment of inertia of a cross-section by splitting it into small elements. Each element contributes to the total area moment of inertia by a quantity equal to its area dA multiplied by y squared, where y is the distance to the reference axis, which is the x-axis in this case. We can sum up the values for all of the small elements to obtain the area moment of inertia for the entire cross-section. It is denoted by the letter I, and because the x-axis is our reference axis, we will give it the subscript x. We can define the area moment of inertia more precisely using integration. And if the y-axis is our reference axis, we can calculate Iy in the same way. The area moment of inertia has the unit of length to the force power, and because of the squared term, it is always a positive quantity. Let's walk through an example where we calculate Ix and Iy values for a rectangular cross-section using those equations. We can consider that the rectangular is made up of multiple thin strips which each have a height equal to dy. Each strip has an area equal to b times dy, which gives us the following integral. The limits of the integral are from the bottom to the top of the rectangle, so from negative h over 2 to h over 2. If we solve this definite integral, we end up with Ix being equal to b multiplied by h to the power 3, divided by 12. We can obtain the equation for Iy by switching the height and the width terms. The area moment of inertia is a particularly important parameter for the analysis of beams and columns. This equation, for example, defines the deflection of a beam for an applied bending moment m. You will notice that the term EI appears in many equations. It is called flexural rigidity. It quantifies the resistance of a beam to bending. As we have just seen, I is the resistance due to the geometry of the beam cross-section, but the stiffness of the beam material also contributes to its total resistance to bending, and is captured by Young's modulus E. Flexural rigidity also appears in the analysis of columns, where it can be used to calculate the critical buckling load. Now we can use an example to illustrate the application of the area moment of inertia. This is a 4-point bending test of a timber beam with a grain running parallel to the beam axis. The beam is made of softwood by class C24. The loading diagram shows the singly supported beam subject to 4-point bending and this loading arrangement. Pair of equal vertical loads is now starting to be applied to the central part of the spaceman. We begin to see the beam bending under the load. This continues until the extreme fiber stresses in the tensile zone reach the failure strength of the wood, and brittle fracture occurs. Now let's slow that down and look closer at the point of failure. We can see bearing deformations accumulate in the loading heads. However, stresses continue to increase in the central part of the beam. Soon, the tensile strength of wood in the bottom fiber is reached, and a faster growing crack develops. In the timber beam, elasticity is the ability of a body to resist the loading influence and to return to its original size and shape when that influence or force is removed. If an applied load reaches the collapse load, the timber beam appears brittle fracture. At this stage, we can use the purely plasticity to estimate the collapse load. The bending yield strength can be calculated as 40 Newton per millimeter squared. According to elasticity theory, we can use the bending yield strength and the area moment of inertia to estimate the elastic load of 16 kN. According to purely plasticity theory, we can use the bending yield strength to estimate the collapse load of 24 kN. This is the force displacement graph. It shows an initial linear elastic response. In a clear wood beam with no defects, the tensile strength is much higher than the compressive strength. So, as the wood in the compressive zone begins to crush, the bending behavior becomes nonlinear. Therefore, some redistribution of stresses takes place until the ultimate tensile strength is reached at around 24 kN, which is the same with our estimation of the collapse load based on the purely plasticity theory. From conclusions what we learned, the area of moment inertia is an important parameter for the analysis of the beam considering elasticity. If we want to know the collapse load of a beam, plastic methods are useful to calculate the plastic bending and to estimate the bearing capacity. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I'm happy to answer any questions. Thanks for your watching.